Hello and welcome to THERMO 2, our problem solving session. In this week 1 session, what we are doing is a review of THERMO 1, and I've chosen a energy equation problem, a problem that involves the energy equation, a problem that I've adapted from a classic textbook problem to represent an hypothetical real-life situation where a scuba tank company decides to try to monitor temperature change inside a scuba tank as they are filling it to estimate the total mass of air that goes inside their tank while they're filling it. So here it is. The problem statement is right there. Initially, what we have is a scuba diving tank. The volume is given to us, 0.1 cubic meter, and it's attached to a very large reservoir. We're going to assume that that very large reservoir doesn't change in state as time goes. Initially, though, that reservoir and the scuba tank are both at steady state and at the same temperature, which presumably is the ambient temperature where they're at, around 20 degrees Celsius, according to this problem. Furthermore, there's some air in the tank already. 100 kilopascal gauge is what it tells us. So that means roughly 2 atmospheres absolute. Time equals 0. A valve that separates the reservoir from the scuba tank is open, and air starts to flow from the big reservoir to the scuba diving tank. Since that air, as it flows, is doing work on the air that's already present inside the scuba tank, flow work, the temperature of the air inside the scuba tank can be expected to go up. And sure enough, our thermocouple inside that tank measures a rise in temperature, instantaneous rise in temperature at time equals 0 after the valve is open of 0.05 degrees Celsius per second. Now that rate would probably go down, the rate of temperature rise would probably go down as time goes on, because eventually, of course, the scuba tank is going to be full, and there will be no pressure difference between the scuba tank and the main reservoir, and there will therefore not be any flow into the scuba tank anymore. That'll be the end of the filling process, if you will, if I'm shooting to put 2 megapascal of air inside the scuba tank. But initially, all we care about is the initial mass flow rate of air inside that tank. So let's get started with that. Okay, so first, for this particular problem, we're going to apply the problem-solving template that we've presented before. And the first step, and I've simply copied it here onto my problem as you normally would as you do the same thing. And I'm jumping right in with step number 1, which is to outline the information that's given to us in the problem in simple point form format, so that it makes it easy to come back to and get the information without having to reread the problem every time. So I'm outlining the tank data that's given to me, namely the volume, the initial pressure, highlighting the fact that it's gauge pressure, not absolute, initial temperature, and I do the same with the reservoir. Okay, here we go. My initial condition is that the temperature is changing inside the scuba tank at the rate of 0.05 degrees Celsius per second. And the whole point of this problem is to figure out what kind of initial mass flow rate into the scuba tank this corresponds to. To sketch what's going on in the problem here, what I'm going to do is a couple of things. First, I'm going to sketch what the reservoir / scuba tank layout probably looks like. I'm making a simplified guess as to what that configuration would be. A simple little sketch here to make it clear what we're doing, and I'm using it as well to highlight what the valid control volume for this problem would be, and I'm making a control volume that goes all the way to the main reservoir and includes all of the scuba tank. Now, it's a good idea at this point to estimate or try to hypothesize how both the mass flow rate and the temperature change of the air inside the scuba tank probably changes as a function of time. And then, of course, once the problem is fully solved, we could come back and verify this. But I find it's a good exercise and hones up your engineering intuition if you try to estimate what that probably would look like. Now, in this case, again, as we said, we're going from a very rapid flow initially when the valve is first open to no flow at all down the line. And so that's a pretty good clue that initially the mass flow rate is going to be maximum, and at a very long time, when the problem comes back to steady state, we'll be back to a mass flow rate of 0, and therefore a change in temperature of 0, and that motivates the shape of the curves that I've chosen here. Step number 4, arguably the most important step here, is to outline and describe very clearly, as much as we can, the assumptions that we use when we solve a problem like this. So we're going to outline the type of models that we're going to be using. We're going to be assuming that the air in there is a perfect gas for sure. We're also going to assume that there is no heat transfer taking place between the scuba tank and the surroundings. Otherwise, the temperature that we're measuring is really somewhat artificial here. It includes that heat transfer. We don't really want to take that into account, at least for this first cut analysis of this problem. Okay. So air being a perfect gas means that it obeys the ideal gas law. I'm outlining some basic data for the ideal gas law here for this tank. We're also going to assume that all the properties are homogeneous within the scuba tank, meaning there's no difference in the density close to the valve as there is to the bottom of the tank. Similarly with the temperature, in other words, the tank is well mixed is what we would say. Okay, it's a perfect gas, so the specific heats are also constant. We'll look them up if we need to down the line. The ratio of specific heats, therefore, is also constant. It's a valve connecting to a tank, so there is no shaft work in this problem. Okay, only flow work. We're also going to assume that the flow going into the tank settles very quickly, so there's no kinetic energy effect to the air inside the tank, and similarly no potential energy effect since the tank is level. It's probably not very high anyway. Finally, we're going to assume that both the flow and the properties are all uniform at the inlet, meaning there's no radial gradient as we look at the pipe itself in terms of its properties, and that's going to make our use of the energy equation a little bit simpler as we move along. Okay, I think that's all we need for assumptions here. Yeah, let's write down this thing about the properties, though. That's an important one. And we'll go back later and add more assumptions if we need to as we solve through the problem. Okay, so as I mentioned earlier, the fact that the temperature is changing gives us a good clue that we're dealing with energy, and so therefore that motivates us to look at the energy equation in Reynolds Transport Theorem form. Certainly for a system like this, an open system like this. Also, we established that the problem is a transient problem, and so we're really going to need to look at all terms of the Reynolds Transport Theorem equation. So I'm going to motivate you to go back to the energy conservation handout that I gave you to figure out which form of the energy equation I might be able to jump to begin with. But to keep things in general right now, I'm going to use the most general form of the Reynolds Transport Theorem for the energy equation that I've talked about before. And this is the one in integral form, and I'm repeating it over here. I'm doing it from memory here, so hopefully I don't make too many mistakes here. Okay, now we're going to be using the Reynolds Transport Theorem in its general form. That includes both the transient component in integral form and the convective component also in integral form, both from your handout, and that must be equal to the net heat transferred into the control volume minus the shaft work out performed by the control volume, and of course in this case based on our assumptions, they are both 0, as we stated above, right? Now, E in the convective term and in the transient term represents the total stored energy, which is itself made up of the thermal energy, the kinetic energy, plus potential energy, and those last two are 0 based on our assumptions, as we've talked about before. Whereas E plus, or whatever is left of E plus P over rho, which is the thermal energy plus the pressure over the density, or the pressure times the specific volume, well, that's the very definition of enthalpy. So we're going to replace that with enthalpy. And of course, in a perfect gas, the enthalpy of the air is going to be Cp times T, right? So, yeah, my assumption is that the properties are all uniform at the inlet means that I can also pull them out of that integral, making my life quite a bit simpler. So, I'm going to start off with the convective term first. And this integral over the entire control surface is really only made up of one important area, and that would be the area where the pipe itself penetrates the control volume. And at that point, I have a velocity that is perpendicular to the control volume surface, and that velocity is normal to the control volume surface at that point. So V dot N is really just equal to the magnitude of V itself, and because V and N are going in opposite direction, the relative angle between both of them is 180 degrees, and the inner product of V dot N therefore includes the cosine of 180 degrees, which is -1, so I end up with simply -1 for V. All this gets pulled out of the integral again because the velocity, the density, and the enthalpy are all uniform, so they're not varying as a function of area. I can pull them out. That's kind of nice because now I've got rho VA as one component. Of course, rho VA is the mass flow rate going into the tank at that point. So I've got the mass flow rate times the enthalpy going into the tank. Now I'm working on the transient term. And the transient term, let's start to play with the integral here again. I've replaced the thermal energy inside the tank by Cv times T, which is what it is for a perfect gas. And now I'm expanding the derivative of m times T. The mass and the temperatures are changing inside the tank, of course. But they are uniform based on my assumption, so I can now simplify or apply the chain rule to mt as I'm taking the derivative, and that's what I've done here. The derivative of m with respect to time is simply m dot. Okay, so now putting those two terms together, the convective term and the transient term together, gives me a single expression, which I have right here. And the whole point of this problem is to figure out what that m dot is at time equals 0. This equation here must be true at all times. All times, this is what we've got. So we see m dot appears twice in that equation here, and we see that dt dt appears once. Well, that's dt dt at time equals 0. Everything's at time equals 0 here, because that's the point in time at which we're interested, 0 plus. So we know everything at this point, really. We can it's just a matter of substituting the data that we have. I'm rearranging it a little bit here to make our life a little bit simpler. And this is the ODE that we would solve if we wanted to figure out the mass flow rate and the mass inside the tank for all times. And that would be an interesting problem if we wanted to take this further and actually implement this for finding out the mass inside the tank as a function of time. But really all we care about at this particular moment is only the mass in the tank at time equals 0. So that's going to make our life a little bit easier. All right, so solving for this mass flow rate at time equals 0, we can isolate that in the boxed equation above and express it in terms of what we know. And so we're going to need the mass at time 0. We haven't calculated that just yet. And everything else, though, we know. For air, gamma is going to be 1.4. the temperature, rate of temperature change initially is 0.05 degrees Celsius per second. That's what was given to us. And the temperature inside the tank initially is 293 degrees Kelvin, or 20 degrees Celsius. So let's figure out what that mass is initially, right? So that's going to be rho times the volume initially, and we know the volume that's given to us. But what about rho? We're going to have to calculate what rho is initially. And we're going to do that knowing that the density the density is that of an ideal gas with a pressure at 100 kilopascal gauge, or 201 kilopascal absolute. All right, so let's substitute everything into the ideal gas law here. Let's make real sure that we keep our unit absolute for temperature specifically, and figure out what the density is. And we get a density that's roughly twice what it would be. We expect the density to be roughly twice what it would be at standard temperature and pressure, which is about 1.2. So twice that, expect something around 2.4. And I'm saying that because the pressure inside the tank is 100 kilopascal gauge, which is really close to 2 atmospheres absolute. So, okay, let's punch those in. What do we get for the density? 2.39 kilograms per meter cubed, so it should be. Let's check out our units. Always good practice here. Newton per meter square on top from our pressure. Newton times meter for joules divided by kilograms. And so the kelvins canceled. So we're left with 2.39 kilograms per meter cube, as we thought, close to what we thought. Okay, so now we know everything. We can solve for the total mass inside the tank, about 0.239 kilograms of air inside the tank before we start to do anything else. Put some equation number here so we know what we're talking about. We're going to substitute that value into equation 1. That's the equation that we have for the transient mass flow rate inside the tank. And that gives us a mass flow rate initially at time equals 0 of the mass of the air inside the tank times dt at time equals 0 times the temperature divided by the temperature at time equals 0. So the rate of mass change inside the tank at time equals 0 is going to be equal to the initial mass inside the tank times the rate of change of temperature inside the tank at time equals 0 divided by the absolute temperature inside the tank at time equals 0 times gamma minus 1, or 1.4 minus 1. Oops, what did I put 0.14 there? That's a typo. Should be 0.4, not 0.14. Now let's look at our units. The kelvins are going to cancel. So I'll end up with kilograms per second, which is what I'm hoping to get right. So 102 times 10 to the minus 6 kilograms per second, or roughly 0.1 gram per second, is what's going into that tank initially. That doesn't sound like a lot of air, doesn't it? Does it? But that's what it is. So if we wanted to know sort of a maximum mass into the tank, we could assume that that rate remains constant for a certain period of time, get the new mass inside the tank, and then basically repeat the entire exercise. We would have to continuously monitor the dt, right? That's what our thermocouple is for. But then we could implement, I hope you can see that how we could implement a process like that to figure out how the mass is actually changing inside the tank as a function of time. And voila. Just running this up here. And we are done. Thank you. Have a great rest of your day, and I hope you enjoyed our first video solution of a problem example. Take care.